Hi everyone, my name is Tariq King and I lead the Quality Center of Excellence over at Ultimate Software. And so today what I want to do is remove a lot of the mystery behind AI-driven test automation. We're hearing a lot about these bots that are testing software, but what exactly are they? How do they work? And one of the cool things that I love about Automation Guild is that we're asked as speakers to show you guys something practical. And so today we're going to do that in a huge way for AI-driven test automation. So let's get into it. The bots are here, there's no doubt. These are two different solutions, one built as an internal tool at Ultimate Software on the left, and the other on the right built by Test.ai, a startup that's doing commercial applications of AI-driven testing. And these bots are exploring the application, discovering elements, seeing what is on the screen just like a human would, and generating some sort of test input. They're using testing techniques. They're doing exploratory testing, trying things, making mistakes, improving and getting better. And so AI-driven testing is real. And we're seeing more and more that there's a lot of companies coming online. And one of the disclaimers I'm going to make right now is that what we're going to show today is not really a standard by any means that every one of these companies is using. The focus of the talk is really to give you an idea of the function of the bots and some approaches to implementing them, so that when people are talking about it, you have a concrete idea of what these things are doing and how they're doing them. So in terms of the agenda, we're going to first get into some of the characteristics of these bots, and then look at some simple reflex bots. Bots that don't require a huge amount of machine learning, but are still considered to be necessary for us to actually execute and drive tests across an application. And then we'll look at how these bots have been enhanced to include artificial intelligence and machine learning, and some of the advances that are making them better and better every day. Then we'll get into the demos and have those takeaways that we're probably looking forward to. All right, so we're hearing a lot about autonomous testing and people are throwing this word around. And so I wanted to start by really just clearing up that definition. And one of the best ways that I can kind of visualize that, and I've used this analogy before when it comes to testing, is the idea of a self-driving car. Driving a car from one point to another point is just a journey similar to what a tester might take from one point in the application to another. And there might be different obstacles along that journey. There might be different threats or risks that you have to look out for, decisions that need to be made. There's aesthetics, right? Things that need to look good if you're going to enjoy your journey, and so on and so forth. The thing about a self-driving car is that it really is doing it on its own. There's some independence and freedom. And so the first point is that self-managing systems, which are autonomous and independent and free, at least to some degree, are important when you start talking about automation. In other words, they need to act independently, or at least have the freedom to do so. And that's what these bots are doing. And we can't really talk about autonomous control and automation in that way without thinking about what are called control systems, and in particular, control loops. And a good example of that in the real world is a thermostat, right? Air conditioning system. This system is somehow monitoring the environment. There's sensors. And it also has a means of affecting the environment through some actuator or effector. And here in this case, the human sets a desired temperature. That's the goal for the system. Maintain this temperature. And the system starts monitoring and taking feedback and turning on and off the air condition to achieve that goal. And it does it by itself. So the bots typically implement functions such as monitoring. So they're looking at the environment and collecting information. And then they're analyzing that information to make decisions, to reason about it. And then they need to somehow devise a plan. So recommending or selecting some procedure to achieve their goals. And then they execute that set of actions that are recommended. And so this idea of monitor, analyze, plan, execute is a core aspect of the functions of these bots. And they all do that with some sort of knowledge. It could be very basic knowledge at the center, or it could be something more complex. And so IBM really coined this monitor, analyze, plan, execute, and knowledge. So in addition to being autonomous, these bots are intelligent, at least to some degree, right? Maybe intelligence should be in quotation marks, but the whole idea here is that they use artificial intelligence and machine learning. And so I wanted to just depict that graphically here. And you should think of AI and artificial intelligence as just this huge umbrella, right? It's the study of getting machines to mimic intelligent behavior. And I used to always say intelligent human behavior, but there's other forms of intelligence besides humans, and actually maybe some humans aren't really always that intelligent. um, but nonetheless, machine learning is a subset of AI, and it deals with the programming model. It deals with how do we get machines to actually improve with experience. And that's really about data, as opposed to giving the machines very specific instructions, do this, do that, do the next. You show the machine different examples of things, and by training it on that data, it can infer the function or the instructions that it needs by mapping those inputs to outputs. Deep learning, on the other hand, is a subset of machine learning, which deals with large scale computation using multiple layered neural networks. Now, there's lots of different approaches to machine learning, and we're not going to cover them here, but it's worth mentioning so that you have a frame of mind that when we start talking about these bots and them using machine learning, like what are some of the things that they're doing? There's Bayesian networks, neural networks, there's clustering, decision trees, reinforcement learning. There's such a wealth of information out there on these topics. So lastly, the bots are agents. They're these autonomous and intelligent entities that, as we mentioned, perceive and act in their environment using sensors and actuators. They direct their activity towards goals and use knowledge and learning to achieve those goals. They can analyze themselves, and this is very key. They look at their own behavior, their errors and success rates, and then they can adapt online, possibly in real time. And then they can be organized with other agents. Just as we collaborate, the bots collaborate, they solve problems at different levels of abstraction. And there are several different types of agents. A simple reflex agent is one that basically looks at some condition, and if it's true, it does some pre-programmed response. So for example, if I throw something at your face, you're likely to blink, right? Your reflexes can kick in and you blink, and that's kind of automatic. And so these agents don't really need a lot of intelligence, but they do need some rules around how to act when certain conditions are in place. Model-based agents, agents a lot of the time will create a model as they see things and observe things, and that's so that at any point in time, if they maybe can't observe something or have partial information, they can actually still operate in those types of conditions. Goal-based agents, right? They have a goal, whether that be some desired temperature or that is to traverse through an application to a particular destination. You can set that goal and have the bots figure out how to achieve that goal. Utility is more of a local optimization problem. So the bots may be in a mode where they're trying to maximize their satisfaction with every given action, right? And maximize utility as an end result. And then last but not least, learning. The bots need to be able to improve with time. All right, so let's go back to 2008, where I was in this building. This is FIU's School of Computing and Information Sciences as part of the engineering college. It was in that building that I was actually building my first bots. My bots were very simple reflex bots, and I think it's a good point of view for us to start understanding how these things work. And so in terms of my research, I was working in the area of autonomic computing. And at the time, I think IBM, HP, Microsoft, they all had their own initiatives around building the future of systems, the next generation of systems. And some of the characteristics of these systems were that they were self-adaptive, right? They could configure themselves, heal themselves, optimize themselves, and protect themselves, and really adapt themselves to changing conditions. And IBM had an architectural blueprint, and they put forward the structure of their agents. They wanted an agent-based approach to do this, and they introduced the concept of an autonomic manager, which could monitor, analyze, plan, execute all around knowledge. And they would do that by monitoring the managed resources of the system, which were either software or hardware components. But what no one was talking about or looking at, even though they were thinking that all these self-star features were great, they weren't considering that if we did this type of dynamic behavior where the system could adapt its behavior and structure at runtime, is that these systems needed to have an implicit self-testing characteristic. And so that's what my research focused on. How can I enable implicit self-testing within these types of systems? So I had to look at how could I build bots to test the bots that were doing this adaptation and test that adaptive behavior. And that was pretty interesting because I had never built a bot to do adaptation. And to my knowledge, no one had ever built a bot to do testing. And so for me, I usually step back when I have a very difficult and challenging problem and start to think about the context that I could at least start my investigation in. And that's where I came up with this idea of a self-testing autonomic container. And this was really just a framework to allow me to investigate building simple reflex bots for testing. But it first started with just building something that could adapt. And so this idea of an autonomic container was one where I just said, well, let's consider having a container that can hold elements. And users can put elements in this container. And as users put elements in the container, the adaptation manager, the bot that's responsible for changing the system, will just monitor how many elements are in the container. And then once the container gets beyond 80% full, it'll dynamically transform the system where it uses a larger container. And I wasn't doing this by allocating more memory. I was actually just simulating a straight code change dynamically at runtime, because I wasn't trying to simulate anything real at this point. I just wanted to have a code change so that I can investigate the thing that was most important to me, which was, could I have bots that actually test this type of adaptive behavior? And how could I enable that? But the first step, nonetheless, was to come up with that adaptation. And I want to just look at the policy. The first thing is that these bots, to do adaptation, needed to look at the container state. And then the analyze function would then say, hey, well, you know what? If you're more than 80% full, that is a symptom that I need to figure out. And so I'll pull, figure that out. When that is true, then I know I need to increase the capacity and do that dynamic change. And then that would trigger the testing. And so in terms of my development of the first bot just to do adaptation, I had a simple goal-based policy that was written in XML, and it kind of mapped to the different functions of the monitor, analyze, plan, and execute. So it's very generic and very flexible. But this wasn't really my focus. The reason that it was flexible is because I needed to apply it to testing. And the first step before I could even think about that was, how can I have autonomous control coordinating the testing process? And I did that with two different types of control loops. The whole idea was that the first control loop would just look to see if the system needed testing, and then try to create some sort of a regression plan for it. So it would say, okay, here's the component that changed, and there was predefined tests that it could pick up and start to execute against the system. And then after that was done, it would need to somehow analyze those test results. And so another loop is about seeing if the test results are available and analyzing them to see if they pass or fail, and if there was adequate test coverage, or maybe you're looking at code coverage, and then decide if we needed to stop testing. And this was, of course, at the lower level where we're executing tests. There's a higher level where you might have an autonomous agent controlling this entire process and maybe doing other things. One of the major contributions that I had, and one thing that can help you understand how these things work, is that I just built a simple object-oriented framework to implement these monitor, analyze, plan, and execute functions. And it's very, very straightforward, and it interfaced with a knowledge base. And that knowledge base was simply just a static representation of those rules. And so I created all these things, and I used this framework not only for the adaptation agents, but to also implement testing. And some of the technologies that I used include Java was the main language for all of the bots in the OO framework. I used the Spring framework to hold components, and I had some components written in Java, some components written in Groovy. And Groovy is a nice dynamic language that at runtime, if I want to swap out, make a code change at runtime without recompiling, you can do that in Groovy. XML, of course, for the policies, and then some of the testing frameworks that I use were JUnit, Cobertura, and Eclipse has a test performance and tools platform that you could use to gather performance metrics. And so those were the first bots, and I built a number of prototypes. Of course, the first one was that autonomic container, which was just this adaptive storage with self-configuration. But later on, I built another set of bots and another prototype by extending that autonomic container to do job scheduling. So you had a container, you had scheduling algorithms like first come, first serve or shortest job first, and those algorithms could be swapped in and out and trigger testing. And that whole job scheduler was really combining self-configuration and self-optimization because the container itself for the job scheduling was an autonomic container. So I kind of built on the first project. And then last but not least, it was really a huge effort to start to apply this to something real. And so I did that in the context of something called a communication virtual machine, which was a collaboration between FIU and Miami Children's Hospital, where we're looking at communication between doctors, EMTs, and people in the operating room to achieve something. And what we would do is adaptive communication, right? And so if we introduced a new person into the call, we might be using different frameworks like Skype or Smack or a native framework that can self-configure and do self-healing if something goes down. All right, so step forward to 2018. And it was back at FIU that I would be privileged to be on this gentleman's committee. This is Diony Santiago. He's a principal architect at Ultimate Software. And he was pursuing his master's at the time in the area of AI-driven test generation. And so a lot of his contributions we're going to talk about now, because you start to see exactly how you can build intelligence into these autonomous agents. And so what we're going to do is really just remove that mask. So at the heart of each of these AI-driven testing bots is machine learning. These bots use machine learning during the exploration of the application, discovering the UI elements. We might use images to train the application to recognize, hey, you know what? This is the shopping cart, or this is the menu button. Or maybe we take information from the DOM and feed it through a decision tree so that it can classify the page title and the error messages. And then it also builds models, and it attaches probabilities to those models and uses statistical techniques. And so a common model used is a state machine, where you can actually map out the states and transitions, and it's very useful for test generation. During the phase where you're generating actions and navigating through the application, you might also use a neural network to randomly initialize the system to take some particular action. And so for example, you might decide, let's pinch to zoom on this menu button. And maybe next time you might tap on it. And the cool thing is that the system is probably gonna not be very good at this initially, but it can learn. So you start to give it direct feedback on the quality of those actions. So you can say, hey, you know what? That was an interesting action, or no, it wasn't. And so you can punish it, for example, for pinching to zoom and reward it for tapping. Now, it's no surprise that the architecture of these bots in terms of their functions is no different from the simple reflex bots. There's still monitoring, analysis, planning, and execution. But now at the core of it is really this artificial brain. And you can think of this artificial brain, instead of static knowledge, as knowledge combined with machine learning. And so we're going to coin this as MAPE plus KML, where there's seeded-based knowledge, but now the system has the ability through machine learning to acquire new knowledge, maintain and update its existing knowledge, and of course share knowledge with other bots and other agents throughout the system. And so this artificial brain is what's really starting to separate the bots of today from the bots of 2008. And so let's look at how the agents actually coordinate and use these artificial brains to do testing. And so at the top level, if we have an agent that's responsible for coordinating the entire testing process, we may have other agents that are more worker level agents that interact with the application under test. Now remember, these are autonomous and independent. And so they can actually go through the application at different stages, do different actions and different behaviors all on their own. And so the top level agent is really responsible for kind of optimizing and coordinating that effort to make it better. And so each of the worker agents might have an initial default mode where they're exploring the application and discovering it. and maybe generating some tests to be executed later. And so let's take a look at this. So as the agents start to do their exploration and generation, they start to create different tests. Now, because they're independent of each other, they might create some tests that are similar to other tests, or maybe even duplicates. And that's not very efficient. And so if we stop to think about the top level agent and the coordination, and we pause this for a second, the coordinator can now look at that list of AI generated tests and start to think about deduplicating them and distributing them to the other agents. And so it starts to say, well, these look like duplicates, but these are unique, and let's start to distribute these to the other agents to be processed. And so now we can see that two of the worker agents on the ends now have queues that are one item long. And so they can switch out of their exploration and generation mode to an execution mode where they're going to run these tests that were generated. And note that the worker agent in the middle still remains pretty static in terms of his execution. He's still in the exploration mode and generation mode. And the coordinator can just start to coordinate each of these things. And so you can start to execute tests on those two workers, and test results can start to trickle in. And meanwhile, the worker agent in the middle can continue on to do his AI-driven test generation. And the coordinator has to be able to look at all of these things and make sure that the system still operates as expected. So let's take a look at these smart test bots in action. And we're going to do that through the demonstration of a prototype called Agent, AI Generation and Exploration in Tests. And the Agent prototype is really a culmination of Diani's work for his master's thesis, as well as a project at Ultimate Software that we call the Form Expert. And now that we've heard an explanation of how these bots really work, we can understand this. In the bottom right-hand corner, on the top line, you can see a coordinator agent that's analyzing the tests that are generated by these 5 worker agents. And on the rest of the screen, you're really seeing these bots, either in exploration or generation or testing mode, execute these test cases and come up with and explore the application. And you'll see them consulting the Form Expert to do things like cross-site scripting, special characters, do different types of equivalence classing and boundary testing. And Diani's work created a language to come up with different flows through the application, right? So if you see a first name and it's required, you now know that, hey, if I try a blank space, like I should expect an error message. So his work enabled a lot of the testing and the Oracle verifications. So I hope to see him on Automation Guild in the future, explaining the intricacies of that work. And so Agent, we used a lot of different technologies. And so we're going to share some of that stuff. First, Python was the language of choice. We built a lot of microservices in Python, and Celery was used as that task management. The Flower component of Celery was that interface that you saw that showed the coordinator and the different agents and help you to visualize that. RabbitMQ was used for our queuing system, and JSON was the payload for a lot of our microservices. Selenium was used behind the scenes to actually execute the test cases against the system under test. And for machine learning, things like scikit-learn, TensorFlow, Keras, NumPy, all these were used to support all the learning components. Now for the big takeaways. What we're doing is contributing to the open source. So this prototype that you just saw, Agent, is completely available as of today on GitHub at github.com/ultimatesoftware/agent. And not only that, for those of you who attended the AI Summit Guild last year, we're also making the demo that we did there, which was a Chrome extension that showed how bots perceive the application and help you to train it. That's also going to be open source. And so all this is packaged up today as part of Automation Guild and released live here. And so go out, get it, explore, dig into it, feel free to extend it and send any feedback. Last but not least, there's so many people that contributed to this. Diani in particular for all his hard work towards his master's thesis. David Adamo, Justin Phillips, Patrick Alt, and Keith Briggs are all engineers and architects at Ultimate Software and leads that are building phenomenal tools. Peter Clark, Diani's advisor and my former advisor for his graduate research, and Jason Arbin, my partner in crime, that's always been willing to share a lot of his knowledge and even a lot of his prototypes and so on and so forth through the open source community. Thank you.